Welcome to the deep dive. Today, we're unpacking a force that silently shapes so much of our digital lives, often without us even realizing it. Think about it. From the moment you ask Siri or Alexa a question to when Netflix suggests your next binge-worthy show or Spotify curates your perfect playlist, deep learning algorithms are working tirelessly behind the scenes.
They really are.
But what is deep learning at its core? And, what were the pivotal moments that transformed it from just a theoretical concept into the indispensable technology it is today?
Indeed, it's been quite a remarkable journey. Deep learning fundamentally is a sophisticated branch of machine learning. It uses artificial neural networks, these digital structures kind of inspired by the human brain,
Right.
but with many layers,
Yeah.
to analyze incredibly diverse forms of data.
Many layers being the key.
Exactly.
Yeah.
This multi-layered approach lets AI uncover these really intricate patterns and abstract features that, well, traditional algorithms might simply miss. They process enormous data sets to drive advancements across fields like image recognition, natural language processing, lots of areas.
Okay.
So our mission today is to guide you through the foundational concepts, the key architectural innovations, and the real-world applications that define deep learning. We want to help you quickly become, well, pretty well informed on this critical area of AI.
That sounds like a perfect framing. So, okay, before we jump into the specific breakthroughs, let's maybe establish the bedrock first. What exactly are these neural networks that are so central to deep learning? It sounds almost sci-fi, but I mean, clearly the impact is very real.
It truly is. At its heart, a neural network is a computational model designed to mimic basically the human brain's structure and function.
Okay.
It consists of interconnected processing units, or neurons, organized into layers. These neurons take input, perform a simple calculation, and then pass the result to the next layer.
Simple calculation, but lots of them.
Lots of them, precisely. Now, the deep learning, that simply refers to the use of multiple layers, often hundreds, sometimes even thousands, within these networks.
Wow, thousands.
Yeah. It's a significant distinction from earlier machine learning programs that might only use one or two layers. And this multi-layered approach, it's fundamental to its power. It allows the network to learn increasingly complex and abstract representations of data.
So it's not just a fancy term. That deep part really defines its capability. Where did this powerful idea first emerge? I mean, was it an overnight sensation?
Oh, far from it, no. The concept has a rich and somewhat tumultuous history, actually. The earliest deep learning models, surprisingly, date back to 1965. They were developed by Alexei Yevgenko and Lapa.
1965, that's way earlier than I thought.
Right. They introduced a method called the group method of data handling, which they saw as a sort of generalization of Frank Rosenblatt's perceptron from 1958.
The perceptron, okay, I've heard of that.
Yeah, Rosenblatt's perceptron itself was an early three-layer model, a significant innovation for its time. His 1962 book even discussed variants with 4 layers.
So the seeds were planted early.
Very early. But despite these sparks, the field soon entered what's widely known as an AI winter.
An AI winter, that sounds chilly and pretty dramatic. What caused that downturn?
Well, it was a period, largely in the 1970s, where public and, scientific sentiment kind of turned against AI.
Why?
Researchers had made some rather grand claims about AI's imminent capabilities, things that were just far from achievable with the computing power and the algorithmic understanding of the era.
Ah, overpromising.
Exactly.
Yeah.
Funding dried up, research slowed significantly.
Yeah.
But, as with many nascent technologies, the field eventually reemerged.
Okay.
This resurgence, primarily in the 1990s and early 2000s, was largely fueled by 2 critical factors.
Right.
Computer hardware becoming powerful enough to actually train larger, more complex networks.
Right, the compute power finally caught up.
Exactly. And also key algorithmic advancements that made training those deep networks practical.
Ah, okay. So better hardware provided the muscle. And what were some of those critical conceptual tools then? The algorithms that allowed researchers to truly leverage that new computational power. Was there like one foundational idea that changed everything?
Absolutely. One of the most critical conceptual tools was backpropagation, or backward propagation error.
Backpropagation. Okay.
This is the fundamental algorithm used to train and optimize deep learning networks. Imagine your network makes a prediction and, well, it's wrong.
Happens all the time when learning.
Right. Backpropagation works by calculating precisely how much each connection or weight in the network contributed to that error. And then it systematically adjusts those weights backward, layer by layer.
So it figures out who messed up and tells them how to fix it.
Pretty much, yeah. It's how the network learns from its mistakes, progressively getting better at its task. It's fascinating. Its underlying mathematical principles of the chain rule can actually be traced back to Gottfried Wilhelm Leibniz in 1673.
Wow, Leibniz from calculus.
The very same. But its modern form, specifically for this kind of automatic differentiation, was formalized by Seppo Linnaanmaa in Finland in 1970, and then popularized for neural networks by researchers like Rumelhart, Hinton, and Williams in 1986.
That's fascinating. So it's essentially a very sophisticated, mathematically grounded trial and error system. Were there other fundamental components that emerged around that time to make these networks more effective?
Yes, definitely. Another vital component is the activation function.
Activation function.
Kunihiko Fukushima, a Japanese researcher, as early as 1969, introduced a concept that eventually evolved into what's now known as the rectified linear unit, or ReLU.
ReLU, okay.
This function has become the most popular activation function for deep learning networks today. It's surprisingly simple, but incredibly effective.
How does it work?
Well, basically, if a neuron's input is positive, it just outputs that value. If the input is 0 or negative, it outputs 0. That's it.
Seems simple enough. Why is that so powerful?
It helps address a really critical issue called the vanishing gradient problem, especially during training.
The vanishing gradient problem, that sounds important, but also, yeah, a bit cryptic. Can you unpack that?
Certainly. So in very deep networks, remember all those layers, the signal used to update the network's learning, we call it the gradient, which comes from backpropagation. That signal can become progressively weaker as it propagates back through many, many layers.
So it fades out.
Exactly. By the time it reaches the early layers, that signal can effectively vanish, meaning those initial layers just stop learning efficiently. They don't get useful feedback.
Ah, okay, so they get stuck.
Right. ReLU, because of its simple nature, helps keep that gradient signal strong and stable. It prevents it from shrinking too much, allowing even very deep networks to learn effectively and, importantly, much more quickly without getting bogged down.
So we have this layered, brain-inspired architecture, refined by backpropagation for learning from errors, and boosted by activation functions like ReLU to keep the learning going. But what's the real power behind having all these layers, the deep part? Why not just have one very, very complex layer?
That's where the true genius of deep really comes into its own. Deep neural networks, or DNNs, with their multiple layers between the input and output, can model incredibly complex nonlinear relationships in data, things that a single layer, no matter how complex, would struggle with.
Nonlinear, meaning not just straight lines, but curves and complex interactions.
Precisely. And they excel at generating what we call compositional models.
Compositional models.
Yeah, think of it like building something complex with Legos. The first layer might identify individual bricks,
Yeah.
the most basic primitives.
Okay, edges, corners.
Exactly. The next layer combines those bricks into simple shapes, maybe like a small wall or a roof piece. Subsequent layers combine those shapes into increasingly complex parts until the whole object, say, a house, is recognized.
Ah, so it builds understanding level by level.
That's it. This hierarchical building of understanding, extracting progressively more abstract features at each layer, is what makes deep networks so powerful. It allows them to model incredibly complex data, like images or speech, with far fewer computational units or neurons than a shallow network would need to achieve similar performance. It makes them exponentially more efficient for certain tasks.
Fewer units, but more layers is the key.
Exactly. This fundamental ability to learn hierarchical representations is a core insight that underpins pretty much all the specific breakthroughs we'll discuss next.
That layered hierarchical understanding is a really powerful idea. Okay, so if that deep architecture itself was the foundational shift, how did we then teach these networks to tackle incredibly specific, almost human-like tasks like seeing the world? I'm thinking about things like our phones recognizing our faces or cars spotting pedestrians. It's often tied to convolutional neural networks, right, CNNs.
You've hit on the perfect segue there.
Yes.
That ability to see is precisely where convolutional neural networks, or CNNs, absolutely revolutionize the field. They are truly the gold standard for image and video processing today.
The gold standard, okay.
Their brilliance lies in their unique architecture, which automatically learns these hierarchical patterns in visual data. They do this through mathematical operations called convolutions.
Convolutions. Sounds mathematical.
It is a bit, yeah. The core idea, without getting too deep into the equation Sij rel I plus mj plus n kmn, is that instead of trying to process an entire image at once, a CNN uses small filters or kernels, that's the k in the equation, to slide across the input image.
Like a little magnifying glass scanning the picture.
Kinda, yeah. And each filter is designed to detect a specific simple feature like a vertical edge, a horizontal edge, or a certain texture. The output S is a feature map showing where those features were found.
Okay, so it breaks the image down into these feature maps.
Exactly. And then you have multiple layers. The first convolutional layer finds simple features. The next layer takes those feature maps as input and uses its own filters to find combinations of those features, maybe corners or simple curves.
Building up complexity.
Precisely. Then you often have pooling layers, which basically summarize regions in the feature maps, making the representation smaller and more robust to small shifts or distortions. And finally, you usually have some fully connected layers at the end, like in a standard neural network, that take all these high-level features and make the final classification, this is a cat, or this is a car.
So it's the structured way of looking at images, breaking them down hierarchically, that has such a massive impact. Where are we seeing the most profound effects of this technology right now?
Oh, the applications are truly transformative. Consider automated quality assurance in software development. CNNs can automatically detect subtle visual bugs in user interfaces like a button being misaligned or text overlapping across lots of different devices and screen sizes. That saves countless hours of manual testing.
That's huge for developers.
Definitely. For augmented reality, frameworks like Apple's ARKit and Google's RCore leverage CNNs for real-time plane detection, finding floors and tables, and object recognition. This makes AR applications far more sophisticated and stable, letting virtual objects interact realistically with the real world.
Right, so the virtual furniture actually sits on the floor.
Exactly. And then on a massive scale, think about platforms like YouTube and Facebook. They rely heavily on CNNs for content moderation, automatically filtering billions of inappropriate images and videos daily. It's a task that would be completely impossible for humans alone, given the sheer volume.
Billions. That's an incredible scale. And I know they've been transformative in more critical, even life-changing fields as well, haven't they?
Absolutely. In medical imaging, CNNs are becoming vital. They assist in diagnostics, detecting subtle signs of diseases like diabetic retinopathy in eye scans, or identifying cancerous regions in pathology slides.
So helping doctors make better diagnoses.
Yes, or at least providing a very powerful second opinion or highlighting areas to focus on. They can assist in identifying skin disorders from photos, or even precisely counting dividing cancer cells in microscopy images to assess how aggressive a tumor is.
Wow.
And perhaps one of the most high-profile applications is in autonomous vehicles. CNNs are absolutely crucial for interpreting the data from the 360-degree cameras and LiDAR systems, enabling real-time object detection.
Like spotting pedestrians and other cars.
Exactly. Systems like YOLO, which stands for You Only Look Once, are key components in self-driving cars. They enable the vehicle to identify everything from other cars, pedestrians, cyclists, to traffic signs and lane markings with astonishing speed and accuracy. Even commercially, way back in the early 2000s, Jan LeCun, a pioneer in CNNs, estimated that CNNs process something like 10% to 20% of all checks written in the U.S., reading the handwritten amounts.
That's amazing. So they were already having a big commercial impact back then.
Yes. And they've achieved superhuman performance in certain tasks, too. Back in 2011, a CNN achieved better-than-human results in traffic sign recognition, and by 2014, in human face recognition as well. The core insight here, really, is that CNNs empowered machines to move beyond simply processing pixels to understanding visual hierarchies, building an internal conceptual representation of the scene.
And it's amazing how this seeing capability has extended into unexpected areas, like protecting our digital infrastructure. You mentioned cybersecurity.
Precisely. CNNs have also had a profound impact on cybersecurity. Think about intrusion detection systems. Modern systems now deploy CNNs to analyze network traffic patterns in real time.
How does that work visually? Isn't network traffic just data packets?
That's a great question. You can actually represent network traffic patterns visually or as grid-like structures where CNNs can find spatial patterns corresponding to certain types of activity. By learning to recognize the visual signature of normal network flow, they can rapidly identify anomalies that might indicate a cyber attack or a data breach.
Interesting, like spotting a weird pattern in the data flow.
Exactly. Similarly, for malware detection, traditional antivirus software often relies on known signatures, which means they miss brand new threats.
Zero-day attacks.
Right. CNN-based systems, however, can sometimes identify previously unseen malicious software. They do this by treating the program's code, or its behavior patterns, as something they can analyze for subtle indicative patterns, even if the code is obfuscated or changed. Companies like Cylance, now part of BlackBerry, and Darktrace have pioneered these approaches, achieving impressively high detection rates, often over 99%, while significantly reducing the number of false alarms. It's really elevated our ability to defend against these constantly evolving digital threats.
Okay, so from seeing the world with CNNs, we move to understanding sequences. Recurrent neural networks, or RNNs, sound like they bring a whole new dimension to AI. We're talking about things like natural language and speech, right? Where context and order are absolutely everything. What's special about RNNs, and how do they differ fundamentally from CNNs?
You've perfectly captured their essence. RNNs are a different architectural paradigm entirely. They're specifically designed for sequential data, where the order of information matters profoundly.
So time matters.
Exactly. While CNNs excel at spatial hierarchies, like pixels arranged in an image, RNNs shine with data that unfolds over time, like text, speech, or financial time series. Their real power lies in their ability to maintain a kind of memory or contextual information through time. They effectively remember previous inputs in a data sequence.
A memory. How does that work?
It means the output at any given step in the sequence, say, predicting the next word in a sentence, is influenced not just by the current input, the current word, but by the entire history of inputs, the preceding words that came before it. This memory makes them ideally suited for tasks where order and context are absolutely paramount.
That concept of memory is fascinating. How does an RNN mathematically hold on to that context over time? It sounds like it needs to keep track of a lot of information.
It does, but in a very elegant way. The core mechanism revolves around what's called a hidden state.
Hidden state.
Okay, you can imagine this hidden state as a compact summary, like a vector of numbers, that represents everything the network has processed up to the current moment in the sequence. At each time step, the RNN takes two things. The current input, like the current word, and the previous hidden state, the memory from the last step.
Okay.
It combines these two using some learned weights and an activation function, often tan, the hyperbolic tangent, to generate a new hidden state.
Yeah.
This new state then does two things. It influences the current output, like predicting the next word, and becomes the memory for the next step in the sequence.
So the memory is constantly being updated with new information.
Exactly. Mathematically, the formula is something like HTST plus HHT1 plus BH. Here, H-T is the new hidden state, X is the current input, HT1 is the previous hidden state, and the W terms are the learned weight matrices. It's this recurrent connection, HE1 feeding into the calculation of H key, that gives them their name and their memory.
That makes sense. And when you mentioned unrolling it.
Right? If you visualize an RNN processing a sequence over time, you can unroll it. It looks like a very deep feed-forward network, where each layer corresponds to a time step. But crucially, the weights, the W matrices, are shared across all these time steps. This parameter sharing is key. It means the network learns rules that apply consistently across the entire sequence, reinforcing that sense of continuous context and memory.
That makes perfect sense for things like understanding language or maybe even analyzing code, right? Where has this ability to streamline sequential data processing made a real impact in our daily lives, maybe particularly in software development?
Oh, it's had a profound effect across numerous workflows. Take automated code completion, for instance. Modern integrated development environments, IDEs, like Visual Studio Code or those from JetBrains.
Yeah, I use those all the time.
Right. They now use RNN-based models, often sophisticated ones like LSTMs or transformers, which build on RNN ideas, to predict what a developer will type next. By understanding the context of your code, the variables you've defined, the functions you're in, they suggest relevant completions, significantly boosting coding efficiency and reducing typos.
It really does feel like magic sometimes.
It's pretty close. Then in operations for DevOps schemes, RNNs are employed for log analysis. Servers generate massive streams of log data.
Tons of it.
Exactly. RNNs can parse these vast logs, learn the patterns of normal system behavior, and then detect subtle anomalies that might indicate system failures, performance bottlenecks, or even security breaches, often long before they cause a major outage.
So finding the needle in the haystack of log files.
Precisely. And even smart debugging is starting to benefit. There are emerging tools using RNNs to analyze program execution, traces the sequence of steps a program took before it crashed to suggest potential locations, and even fixes for bugs. This could drastically reduce the often frustrating time developers spend debugging complex software.
That truly sounds like it's making developers' lives significantly easier. But it also sounds like this is the underlying tech behind our virtual assistants, like Siri and Alexa, and maybe those uncannily good recommendation systems on Netflix.
You're absolutely right on both counts. RNNs, especially advanced variants, have transformed modern recommendation systems, unlike older approaches that might have looked at your purchases or views independently.
Right, like collaborative filtering?
Yeah. RNN-based systems capture the evolving preferences of users over time. They understand your viewing or purchasing patterns as a sequence. They consider not just what you liked, but the order in which you interact with items.
So the journey matters.
The journey matters. Netflix, for example, reported significant improvements in recommendation relevance, something like 40%, by using models that understand these sequential viewing histories. It helps them suggest something relevant to what you just watched, or predict what phase of interest you might be entering.
That makes sense. And predictive UIs.
Yes. In user interface design, RNNs enable predictive UIs that anticipate user needs. Google's Smart Compose feature in Gmail is a prime example. It uses RNNs, or more likely transformer models now, to predict and suggest the rest of your sentence as you type, learning from billions of email interactions.
I use that all the time. It's surprisingly good.
It learns common phrases and your personal style. Amazon also reportedly uses similar concepts to dynamically reorganize elements on its pages based on predicted user intent, trying to show you what you're most likely looking for next, creating more intuitive and responsive user experiences.
So it's not just about what you like, but the flow of how you interact. And this memory and sequence understanding is clearly central to natural language processing, NLP.
Indeed. NLP has been absolutely revolutionized by RNNs and their successors. They've fundamentally changed how machines understand and interact with human language.
How so?
Well, they're critical to conversational AI and chatbots. They allow the AI to remember the context of the conversation over multiple turns, making the interaction feel much more natural and less like talking to a machine with no memory.
Right, so it remembers what you asked 3 questions ago.
Ideally, yes. For machine translation, modern systems like Google Neural Machine Translation, or GNMT, moved away from phrase-based statistical methods to using deep learning, particularly stacked LSTMs initially. These systems learn from millions of sentence pairs and translate entire sentences at once, capturing context, nuance, and grammar, far better than older methods that translated words or short phrases in isolation.
That was a huge leap in quality, wasn't it?
A massive leap. RNNs also power sentiment analysis, allowing businesses to automatically interpret and categorize opinions expressed in vast amounts of text data, like product reviews or social media posts, providing valuable insights into customer satisfaction or brand perception. And of course, as you mentioned, they are foundational to voice recognition for virtual assistants like Siri, Alexa, and Google Assistant. Converting the sequence of sound waves into a sequence of words requires understanding temporal patterns, which is exactly what RNNs are good at. All the major commercial speech recognition systems today are based on deep learning, particularly using LSTMs or related architectures. Google reported a huge 49% improvement in their speech recognition accuracy back in 2015 when they switched to an LSTM-based model.
Wow, 49%. That's transformative. And speaking of LSTM's long short-term memory, that's a particularly powerful variant you mentioned a few times. What makes them so special compared to basic RNNs?
LSTMs are a really crucial evolutionary step for RNNs. They were developed back in 1995 by Sepp Hochreiter and Jürgen Schmidhuber, specifically to overcome the more severe vanishing gradient problem that plagued simpler RNNs.
Ah, the vanishing gradient. Again, it was worse for RNNs.
Yes, especially when dealing with very long sequences. Simple RNNs struggle to capture dependencies between elements that are far apart in the sequence.
Yeah.
Their memory tends to be short-term. LSTMs address this by introducing a more complex internal structure with special units called gates.
Gates, like controlling the flow of information.
Exactly. They have an input gate, an output gate, and crucially, a forget gate. These gates are like little neural networks themselves, and they learn to control what information is allowed into the cell's memory state, what information is let out to influence the output, and critically, what information should be forgotten or erased from the memory state.
So they can selectively remember important things from way back and forget irrelevant details.
Precisely. This gives them a much longer, effective memory, allowing them to model long-range dependencies in sequences much better than basic RNNs. This was a huge breakthrough. In 2009, an LSTM actually became the first RNN to win an international pattern recognition contest, specifically in connected handwriting recognition. That was a historical milestone that truly cemented their capabilities and paved the way for their widespread adoption. The core insight of RNNs, especially enhanced by LSTMs, is that they endowed AI with the ability to reason over time to understand the narrative and flow of information, not just static independent inputs.
That's incredible, really giving machines a sense of narrative, a memory over time. Okay, so if CNNs help computers see and RNNs help them understand sequences in time, the next breakthrough takes it a step further. Generative adversarial networks, or GANs, they help computers create. This sounds like the realm of deepfakes and AI art generators. How does this adversarial process actually work? It sounds competitive.
GANs are, without a doubt, one of the most creative and truly fascinating breakthroughs in deep learning in the last decade. They were introduced by Ian Goodfellow and his colleagues back in 2014. And yes, adversarial is the key word. They consist of two competing neural networks, a generator and a discriminator.
Okay, two networks fighting it out.
Pretty much.
Cute.
Imagine it as a continuous game of cat and mouse, or maybe an art forger and an art detective. The generator network's job is to create synthetic data, say an image that looks like a real photograph, but is actually completely fabricated.
Right, the forger.
Right. The discriminator network's job is to act as the discerning critic, the detective. It's trained on real data, actual photographs in this example, and its task is to distinguish between the real data and the fake data produced by the generator. It outputs a probability, is this image real or fake?
So they're constantly trying to trick each other, always trying to one-up the other. How does that lead to good results?
Precisely. They compete in what's mathematically termed a minimax game. The generator tries to minimize the probability that the discriminator detects its fakes, essentially trying to maximize the discriminator's error. The discriminator tries to maximize its ability to correctly classify real and fake, minimizing its error.
A push and pull.
Exactly. This adversarial process forces both networks to become incredibly good at their respective tasks. The generator learns to produce increasingly realistic and convincing synthetic data to fool the discriminator. And the discriminator becomes highly adept at identifying even subtle imperfections or statistical giveaways that mark an image as fake.
So they both get better together through competition.
Right. The end result, when training works well, is that the generator becomes capable of producing remarkably realistic synthetic data, images, audio, text, you name it, that can be very difficult for even humans to distinguish from real data. The core insight here is that GANs introduced a brilliant competitive learning framework that enabled AI to create novel, highly realistic content. It was a major step from just recognizing patterns to truly generating new instances.
That's a truly ingenious setup. What kind of impact has this had on content creation and design, maybe particularly thinking about software development or related fields?
Oh, the impact has been revolutionary, really driving innovation across numerous creative domains. In game development, for instance, companies like NVIDIA have heavily invested in GANs, particularly their Style GAN architecture. They use them to create incredibly realistic textures, character faces, and even detailed environment assets. This can dramatically reduce the enormous amount of manual labor typically involved in building vast, visually rich virtual worlds.
So generating assets automatically.
Yes, or at least providing highly realistic starting points for artists. But it's perhaps in digital art and content creation where GANs, and now more recently the diffusion models that have evolved from them, have truly democratized access to powerful creative tools.
You mean things like DALL-E and Midjourney?
Exactly. Text-to-image synthesis models like DALL-E, Midjourney, and Stable Diffusion allow anyone, including developers, to generate sophisticated images simply by typing a text description.
A cat wearing a hat riding a bicycle.
And you get a surprisingly coherent image. Companies like Runway ML and others are providing APIs for these models, making these powerful generative capabilities easily accessible for developers to integrate into their own applications without needing deep AI expertise themselves. This allows for rapid prototyping of visuals, generating custom icons or illustrations, or even creating entire libraries of synthetic data for training other AI models.
That's incredibly powerful for prototyping and even production. And beyond the purely creative applications, I know GANs have found some critical uses in fields like medicine too, haven't they?
Indeed. In medical image augmentation, GANs are proving very useful. Generating realistic medical images like X-rays or MRI scans is incredibly valuable.
Why? Don't we have enough real scans?
Often, for rare diseases or specific conditions, the amount of available training data for AI diagnostic systems is limited. GANs can be used to produce artificial yet highly realistic medical images that accurately reflect the characteristics of a particular condition. This artificially expands the dataset, which in turn helps train diagnostic AI networks more effectively and robustly, making them more accurate, especially for those rare cases.
So generating data to improve other AI, that's clever.
It is. Now, of course, we have to acknowledge that technology also underpins the creation of deepfakes, highly realistic fake videos or audio recordings.
Yeah, that's the concerning side.
Definitely. Deepfakes have raised significant concerns about misinformation, identity theft, and other illicit uses, and has spurred a lot of research into automatic detection methods. But the underlying generative power of GANs, and especially the diffusion models that have now often eclipsed GANs in image quality and training stability, like those powering Delay 2 and Stable Diffusion, continues to drive innovation across many beneficial applications.
Okay, moving on to our fifth breakthrough. This next one, reinforcement learning, really feels like it mimics how humans or even animals learn, through trial and error, getting rewards for good actions and maybe penalties for bad ones. Tell us about its impact. It sounds like a real departure from just processing existing data like CNNs or RNNs do.
Reinforcement learning, or RL, is indeed quite distinct in its approach. It focuses on learning by doing, learning by experience. It allows machines, or agents as they're called in RL terminology, to learn how to make optimal sequences of decisions. By interacting directly with an environment, the agent performs actions within that environment, observes the consequences of those actions, and receives feedback in the form of rewards or penalties.
Like training a dog with treats.
That's a classic analogy, yes. Over time, through repeated trials and adjustments based on the feedback received, the agent optimizes its actions to maximize its total cumulative reward. Essentially, it learns a policy, which is basically a strategy or a mapping from situations, states, to actions for operating optimally in that specific environment to achieve a long-term goal. The core insight of RL is that it provides a powerful framework for AI to learn complex, goal-oriented behaviors autonomously, simply by interacting with its world, without needing labeled examples of correct actions for every situation.
So it's constantly experimenting, trying things out, and refining its approach based on whether it gets a treat or not. How is that formalized? You mentioned this continuous cycle of action and feedback.
Exactly. The standard mathematical framework for formalizing this is often the Markov decision process, or MDP.
MDP?
An MDP is typically defined by a few key components: a set of possible states, S, the agent can be in, a set of actions, A, the agent can take in each state, a transition probability, P, which defines the probability of moving from one state to another given an action, a reward function that gives the immediate reward received for taking an action in a state, and sometimes a discount factor, gamma, gadmoaga, which determines how much the agent values future rewards compared to immediate ones.
So it balances short-term game versus long-term goals?
Precisely. The ultimate goal for the RL agent is to learn a policy often denoted as pi, which is a strategy telling it which action to take in any given state in order to maximize the total expected cumulative discounted reward over time. It's a really powerful and general framework for tackling dynamic decision-making problems under uncertainty.
This sounds incredibly powerful for automating complex decision-making processes, especially in environments that are constantly changing or where the rules aren't perfectly known beforehand. Where has RL made a significant practical impact already?
It's transforming some fundamental infrastructure management, for example. Google famously utilized RL algorithms to optimize the cooling systems in their massive data centers.
Cooling data centers. How has RL helped there?
Well, cooling is a huge energy cost. The RL agent learned how to dynamically adjust hundreds of variables in the cooling system: pumps, fans, vents based on real-time temperature sensor data, serve load predictions, and weather forecasts. By learning an optimal control policy through interaction, it achieved an impressive 40% reduction in energy consumption for cooling while maintaining safe operating temperatures for the servers.
40%, that's massive savings.
Huge. In software development itself, RL agents are being explored for automated software testing. Tools like Microsoft's Wrestler, for example, use RL principles to intelligently explore the possible states and API calls of a web service to discover bugs or security vulnerabilities more effectively than random or predefined testing scripts.
So it learns how to break the software.
In a sense, yes. It learns how to navigate the application's state space to find problematic edge cases. Cloud providers also increasingly implement RL for dynamic resource allocation. They use it to automatically scale computing resources like virtual machines or database capacity up or down based on fluctuating demand patterns, optimizing both cost for the provider and performance for the end users of countless online services.
Beyond efficiency, I know RL has been a build-a-superstar in the world of games, hasn't it? That's where we often see AI truly outperforming humans in very complex tasks.
Absolutely. The gaming world has been a primary proving ground and a source of major breakthroughs for RL, partly because games provide complex, well-defined environments with clear reward signals.
Right, like winning or losing.
Exactly. DeepMind's AlphaGo is the most famous example, of course. It defeated Lee Sedol, the world Go champion, back in 2016. Go is a game with more possible board positions than atoms in the universe, previously thought to require uniquely human intuition and creativity.
That was a landmark moment.
It really was. And even more impressively, their subsequent system, AlphaZero, learned at Go, Shogi, Japanese chess, and traditional chess entirely through self-play. It started knowing only the rules and played millions of games against itself, discovering strategies and principles that surpass centuries of human knowledge in those games.
Just learning by playing itself. Incredible.
It is. And beyond board games, AI agents trained with deep reinforcement learning have even outmaneuvered top human players in complex real-time strategy video games like StarCraft II and first-person shooters like Quake Third Arena and Capture the Flag modes. There was even a simulation called Alpha Dogfight, sponsored by the U.S. Defense Advanced Research Projects Agency, DARPA, where an RL agent consistently defeated an experienced human F-16 fighter pilot in simulated aerial combat scenarios.
Wow. That demonstrates RL's capacity to master highly complex, dynamic, strategic environments.
Definitely.
That adaptability to complex, real-time situations seems like its biggest strength, and it must extend far beyond just games into real-world systems.
It truly does. This ability to learn and adapt in real time translates into systems that can continuously optimize their performance in dynamic real-world scenarios. Netflix, for instance, reportedly employs RL algorithms to dynamically adjust video streaming quality.
How so?
Based on fluctuating network conditions, the user's device capabilities, and maybe even inferred user preferences, the RL agent learns a policy to select the optimal bitrate and resolution to provide the best possible viewing experience while minimizing buffering interruptions.
So it's constantly learning how to stream better for my connection.
Essentially, yes. In cybersecurity, Darktrace's enterprise immune system is an interesting example. It uses unsupervised learning and reinforcement learning concepts to model the normal behavior of a network and its users, and then detect and respond to anomalous activities that might indicate a threat, adapting to new attack vectors in real time without needing predefined rules for every possible threat.
Adapting to threats as they emerge.
That's the idea. And in a really fascinating area like compiler optimization, translating high-level code into efficient machine code, RL is making inroads. Writing optimal compiler heuristics is notoriously difficult.
Yeah, it's a bit of a black art.
Right. But systems like Facebook's Tensor Comprehensions and Google's TensorFlow compiler use RL to automatically discover optimal sequences of code transformations for specific hardware architectures, like GPUs or TPUs. They've shown they can often outperform meticulously hand-tuned human heuristics by 5–20% in terms of final execution speed.
So AI optimizing code for AI hardware.
Exactly. And we even see it applied quite successfully in robotics. There's a bipedal robot named Cassie, developed at Oregon State University, that learned robust walking, running, and even stair climbing behaviors using deep reinforcement learning and simulation first, then transferred to the real robot. The U.S. Department of Defense has also explored RL for training robots, using systems like Deep Tamer, where robots can learn complex tasks relatively quickly by observing human demonstrations and receiving simple feedback signals like good or bad.
These applications are genuinely mind-boggling, showing machines learning and adapting to entirely new situations through interaction. But with such incredible power, I have to imagine there are some serious challenges and significant ethical implications that we need to consider as this technology becomes more and more ingrained in our lives.
Absolutely. You're right to raise that. While deep learning offers immense potential and has driven these profound innovations we've discussed, it's absolutely crucial to address its inherent limitations and potential pitfalls responsibly. These aren't just technical hurdles, they carry significant societal and ethical weight.
Okay, let's start with what's often called the black box problem. We hear that term a lot. What is that exactly, and why is it such a concern, especially as these systems start making more critical decisions that affect people's lives?
The black box problem refers directly to the lack of interpretability in many deep learning models, especially the very deep neural networks, because they have millions, sometimes billions, of parameters interacting in complex, nonlinear ways across many layers.
Like we discussed with DNNs.
Exactly. It becomes incredibly difficult, often practically impossible, for humans to understand exactly how they arrive at a specific decision or prediction. You feed data in one end, you get an answer out the other, but the reasoning process inside is opaque.
Hidden.
Hidden, yes. And this opaqueness has significant consequences. It makes it really challenging to identify the root cause if the model makes an error. It's hard to uncover if there are innate biases lurking within its decision-making process, biases it might have picked up from the training data. And it's difficult to ensure that the model's reasoning actually aligns with our ethical principles or safety standards.
Especially in important areas.
Absolutely. In high-stakes fields like healthcare, is the AI recommending the right treatment for the right reasons? In finance, is it denying loans fairly? Or in autonomous driving, where a wrong decision can have fatal consequences, understanding why the AI decided to swerve or brake is critical for debugging, improvement, and establishing trust. Not understanding the why is a major impediment to reliable and widespread deployment. It highlights this fundamental trade-off we often face. Frequently, the more complex and accurate a model becomes, the less interpretable it tends to be.
That's a tough trade-off. And beyond understanding how they work, there's the sheer effort and resources required to get them to work in the first place, right? You mentioned the computational cost earlier. That alone seems like a huge barrier.
Indeed, it's a major factor. Training large, deep learning models is tremendously computationally expensive. They demand very powerful hardware, especially graphics processing units, GPUs, or increasingly specialized chips like TPUs, and they require vast amounts of memory. The training process itself can consume significant amounts of time, days, weeks, even months, for the largest models, and consequently, a lot of money and electrical energy.
Energy consumption is a big one, too.
A very big one, with environmental implications. OpenAI, for example, published some analysis showing a staggering 300,000-fold increase in the amount of computation used in the largest AI training runs between 2012 and 2017. They found the compute used was doubling roughly every 3.4 months, far outpacing Moore's law.
Wow, 300,000 times.
Yeah. Now, this intense demand has, as a positive side effect, spurred huge innovation in hardware. We're seeing the rise of specialized hardware like neural processing units, NPUs, and smartphones, like from Huawei or Apple, and dedicated tensor processing units, TPUs, in data centers, like Google Clouds. There's even research into things like integrated photonic hardware accelerators, using light instead of electricity, which promise dramatically reduced energy consumption in the future. So while it's a challenge, it's also a powerful driver for hardware innovation.
So the hardware is constantly evolving to try and keep up. But even with powerful hardware, I've heard about other potential pitfalls during training, like overfitting. What does that mean for a model's reliability in the real world?
Overfitting is a very common and critical challenge in all of machine learning, but especially potent in deep learning due to the model's high capacity. It occurs when a model learns the training data too well.
Too well? How can it learn too well?
It starts to memorize the specific examples, the noise, and the random quirks present in that particular training data set, rather than learning the underlying general patterns and relationships in the data that you actually wanted to capture.
So it focuses on the specifics, not the general rules.
Exactly. The consequence is that while the model might perform excellently, even perfectly, on the data it was trained on, its usefulness on new, unseen data, which is what you care about in the real world, is severely limited. It fails to generalize.
So it won't work well when deployed.
Right. It might perform poorly or unpredictably. It's like studying for a history test by just memorizing the exact sequence of words in one specific textbook chapter, instead of actually understanding the historical events and their causes. You might ace a test with questions taken verbatim from that chapter, but you'll likely fail a test that asks slightly different questions about the same events because you didn't grasp the underlying concepts. Preventing overfitting requires careful techniques like regularization, using validation data sets, and sometimes getting more diverse training data.
And the data itself, that seems like it can be a source of fundamental problems, especially regarding bias. It feels like the old adage, garbage in, garbage out, applies here, but potentially with much more significant real-world consequences, right?
Absolutely. That adage is perhaps more relevant here than ever. Deep learning models are fundamentally shaped by the data they are trained on. They learn patterns, correlations, and unfortunately also any biases present in that data.
So if the data is biased, the AI will be biased.
Exactly. If the training data reflects historical societal inequalities or underrepresents certain demographics or contains prejudice associations, the models trained on it will inevitably learn and likely even amplify those biases. This can lead to poor, unfair, or discriminatory outcomes for specific groups when the AI is deployed.
Can you give an example?
Sure. There have been well-documented cases. For instance, facial recognition systems have shown lower accuracy rates for individuals with darker skin tones or for women, often linked to imbalanced training data sets dominated by images of lighter-skinned males. A 2019 article in the Washington Post highlighted the significant racial bias found in a widely used healthcare algorithm in the U.S., which was systematically disadvantaging Black patients in accessing care coordination programs because it used healthcare costs as a proxy for health needs, and Black patients historically incurred lower costs for the same level of illness.
That's deeply concerning.
It is. It really underscores the critical need for meticulous human oversight throughout the entire pipeline, from data collection and annotation, through model development and testing, and into deployment and monitoring. We need to actively scrutinize data for potential biases, develop techniques to mitigate those biases in models, and ensure fairness and equity are primary considerations. It also highlights the ethics around data collection itself. Deep learning relies heavily on human-created or annotated data, often generated through microwork platforms, social media tagging, or even our interactions with quantified self-devices, raising questions about labor practices and data ownership.
Given all these complexities and the potential for bias or error, it sounds like these powerful AI systems could also become targets themselves for malicious actors. Are they vulnerable to cyber threats in new ways we haven't seen before?
Unfortunately, yes. That's another significant area of concern. Artificial neural networks, despite their power, are indeed vulnerable to various forms of hacks and deception, collectively known as adversarial attacks.
And adversarial attacks, like the JANs, but for malicious purposes.
Sort of. But here the attackers is trying to fool a trained model, not compete during training. Attackers can exploit the subtle patterns and shortcuts these systems sometimes rely on to function. They can make tiny, often imperceptible changes to the input data, like modifying a few pixels in an image, adding a minuscule amount of noise to an audio signal, changes that are usually completely undetectable to a human observer.
Okay.
But these subtle perturbations can cause the ANN to completely misclassify the input or perform some other unintended action.
Really? Tiny changes can do that.
Yes. Researchers have demonstrated this repeatedly. For example, they've successfully deceived state-of-the-art image classification systems by adding specially crafted, almost invisible noise patterns to an image of a panda, causing the system to classify it with high confidence as a given. Or, more worryingly, by putting small, strategically placed stickers on a stop sign, causing an autonomous vehicle's perception system to misclassify it as a speed limit sign.
That's terrifying for self-driving cars.
It is a major safety concern. Others have shown how you can embed hidden voice commands into seemingly innocuous audio like music or background noise that humans don't consciously perceive, but that virtual assistants like Alexa or Siri will pick up and execute, potentially opening malicious web pages or making unauthorized purchases.
Wow. So they can be manipulated in sneaky ways.
Very sneaky ways. There's also the threat of data poisoning, where an attacker tries to inject carefully crafted malicious examples into the model's training data over time. The goal is to corrupt the learning process itself, perhaps preventing the model from ever achieving mastery on its intended task, or implanting a specific vulnerability or backdoor that the attacker can exploit later.
So sabotaging the training.
Exactly. This creates an ongoing arms race, much like we see in traditional malware defense. As attackers develop new ways to fool AI systems, defenders need to develop robust countermeasures, like adversarial training, training models on adversarial examples to make them more resilient, input sanitization, and anomaly detection. It's a dynamic and challenging area.
And even without malicious intent, you mentioned that these models can sometimes exhibit strange or limited behaviors, almost like a lack of common sense, despite their impressive capabilities on specific tasks.
That's also correct, and it's an important limitation to keep in mind. Despite their often superhuman performance on benchmark tasks, deep neural networks can sometimes behave in ways that reveal a lack of deeper understanding. For example, they might confidently classify completely unrecognizable images that are just random noise to a human, as belonging to a familiar object category with very high probability.
So they see patterns where none exist.
Or they latch onto superficial statistical correlations rather than meaningful features. Conversely, as we discussed with adversarial examples, they can wildly misclassify images due to minuscule perturbations that are completely irrelevant to a human. This indicates that they don't always possess a robust human-like understanding of the data they process. Their knowledge can be brittle.
Not really grasping the concepts.
Often, yes. They might learn statistical correlations very well, but not necessarily causal relationships or abstract concepts in the way humans do. This can fundamentally limit their utility and reliability in highly sensitive applications, where nuanced understanding, reasoning, or true common sense is critical. Think like complex legal document analysis, truly empathetic customer service chatbots, or situations requiring creative problem-solving outside their training distribution. It's a crucial reminder that while these systems are incredibly powerful pattern-matching machines, they are not yet sentient or truly intelligent in a general human sense, and their mastery can be surprisingly incomplete or fragile in certain contexts.
Okay, so we've covered the breakthroughs and also some pretty significant challenges. Looking ahead now, what's on the horizon for deep learning? Where is this incredible yet complex technology heading next beyond these current hurdles? How will it continue to shape our world and maybe overcome some of these limitations?
The field is continuously evolving at just a breathtaking pace. It feels like breakthroughs happen almost weekly sometimes. And several exciting trends suggest we're heading towards even more profound transformations, not just in software development, but across science, industry, and daily life. It's not just about refining the methods we have, but exploring entirely new paradigms for how AI learns, reasons, and interacts with the world and with us.
Okay, that sounds exciting. Tell us about some of these new directions. What comes next after mastering sight and language sequences?
Well, one major trend that's really gaining momentum is multimodal learning.
Multimodal, meaning multiple types of data.
Exactly. This involves developing AI systems that can process, understand, and crucially, correlate information from multiple types of data. Simultaneously think text, images, audio, video, maybe even sensor data like temperature or motion. Much like humans, naturally integrate information from our different senses to understand the world.
So an AI that can watch a video, listen to the audio track, and read captions all at the same time.
Precisely. And understand the connections between them. Imagine an AI that can understand a spoken conversation while also interpreting the speaker's facial expressions for emotional cues, and maybe analyzing objects or context in the visual background, all feeding into a richer, more holistic understanding.
What's the potential impact of that?
It has the potential to completely revolutionize natural human-computer interaction, making interfaces much more intuitive, context-aware, and adaptable. It could also be huge for accessibility, allowing applications to cater to diverse user needs and preferences by leveraging multiple communication channels. It's about moving towards AI that understands complex, real-world context across various forms of communication, much more like humans do. Another really fascinating area, pushing the boundaries of hardware itself, is neuromorphic computing.
Neuromorphic sounds like brain-shaped computing.
That's pretty much the idea. This isn't just about software algorithms. It's about designing computer hardware chips that physically mimic the structure and function of biological neural systems, like the brain's network of neurons and synapses.
Why do that? What's the benefit over current GPU SDPUs?
The primary goal is energy efficiency. Biological brains are incredibly powerful computers, yet they consume tiny amounts of power compared to today's AI hardware. Neuromorphic chips aim to replicate that low-power, event-driven processing style. If successful, this could dramatically reduce the energy consumption of sophisticated AI systems.
Which would address that huge computational cost issue we talked about.
Exactly. It could potentially enable sophisticated deep learning capabilities, complex real-time analysis, to run efficiently directly on tiny low-power edge devices. Think sensors, wearables, smartphones, maybe even implants, without needing constant connection to powerful cloud servers. This could extend AI-enhanced software capabilities into virtually every aspect of our physical environment in a much more distributed and power-conscious way.
That could really change where and how AI is used. And what about that black box problem we just spent time on? Are there serious efforts to make AI more transparent and understandable, not just more powerful or efficient?
Absolutely, and that's a critical area of focus. This leads us directly to the burgeoning field of explainable AI, or XAI, and the related concept of model interpretability.
Explainable AI.
The core goal here is precisely what you said. To make AI systems, particularly complex deep learning models, more transparent, understandable, and ultimately trustworthy, we need to be able to peek inside the black box, or at least get reliable explanations for its decisions.
How are researchers approaching that?
There are several approaches. One is developing inherently interpretable models whose structure itself lends insight into the decision-making process, like certain types of rule-based systems or models using attention mechanisms, which highlight which parts of the input data were most influential for a given output. Another approach involves developing post hoc explanation algorithms that can analyze a pre-trained black box model and generate explanations for its specific predictions.
Like asking the AI, why did you decide that?
Kind of, yes. Techniques like LIME or SHAP try to approximate the complex model's behavior locally around a specific prediction. And methods like saliency maps can visually highlight the pixels in an image that a CNN focused on most when making a classification.
Why is this so important?
It's crucial for several reasons. It helps developers debug models and identify failures or biases. It helps domain experts, like doctors or scientists, validate whether the AI is reasoning correctly. It helps build trust with end users and regulators, and it enhances accountability when AI systems are used for critical decisions. It's really about moving towards AI systems we can understand and safely rely on.
Beyond XAI and multimodal learning, are there more, maybe slightly more speculative or further out cutting-edge concepts being worked on?
Definitely. The research landscape is incredibly vibrant. There's intense theoretical and early experimental research into quantum neural networks.
Quantum computing meets AI.
Exactly. The idea is to leverage the principles of quantum mechanics superposition, entanglement for computation within neural network structures. It's still very early days, and building practical quantum computers is a huge challenge in itself. But the potential is there for creating immensely powerful future models that could perhaps solve certain types of problems, like optimization or simulating quantum systems, that are currently intractable for even our largest classical deep learning systems.
Fascinating. Anything else?
Another area gaining traction is Bayesian neural networks. Standard neural networks learn fixed point estimates for their weights. Bayesian NNs instead learn probability distributions over their weights.
What's the advantage of that?
It allows them to represent uncertainty much more effectively. Instead of just giving a single prediction, they can provide a measure of confidence or uncertainty associated with that prediction. This is crucial for applications where knowing how sure the model is just as important as the prediction itself. Think medical diagnosis or financial forecasting. They tend to be more robust to overfitting and can handle smaller data sets better.
So, more reliable predictions. And it seems AI isn't just being used for applications anymore, but it's actually turning its capabilities towards accelerating scientific discovery itself.
That's a huge and incredibly exciting development. AI for science. We're seeing deep learning become a powerful tool for scientists across almost every discipline.
Like what?
Well, in materials science, Google DeepMind recently announced their Genome system. It used deep learning to predict the stability of millions of hypothetical crystal structures, leading to the discovery of over 2 million new, potentially stable materials. That's nearly an order of magnitude more than previously known.
2 million new materials. How did they validate that?
They used automated robotic labs to actually synthesize and test a subset of these predicted materials and found a high success rate, around 71% for the initial set reported. And importantly, they've shared this massive database of potentially stable materials publicly to try and expedite innovation in areas like battery technology, superconductors, and solar cells, potentially minimizing or even eliminating years of manual lab work.
That's incredible acceleration. What about biology and medicine?
Huge impacts there, too. In drug discovery, researchers are using generative AI models, similar to those used for images, but adapted for molecules, to design entirely novel antibiotic candidates. Some have already shown effectiveness against dangerous drug-resistant bacteria like MRSA in lab tests and early animal models. Machine learning models are also being used to optimize the design of mRNA vaccines for better stability and efficacy. Graph neural networks are predicting the toxicity of potential drug compounds, and generative models are producing novel molecules that have been successfully validated in mice.
And AlphaFold, right? That makes huge news.
Absolutely. AlphaFold 2, also from DeepMind, achieved unprecedented accuracy in predicting the 3D structure of proteins directly from their amino acid sequence. This solved a grand challenge in biology that had puzzled scientists for 50 years. Accurate protein structures are crucial for understanding biological mechanisms and designing targeted drugs. AlphaFold has made its predictions freely available, revolutionizing structural biology practically overnight.
It's truly helping us solve fundamental scientific problems faster than ever before. It feels like a paradigm shift.
It really does. We're also seeing deep learning models like Google DeepMind's GraphCast predicting global weather patterns up to 10 days ahead in under a minute on a single machine, with accuracy rivaling or sometimes exceeding traditional, computationally intensive physics-based numerical weather prediction systems that run on massive supercomputers.
Predicting weather faster and better with AI.
It seems so, yes. In physics and engineering, researchers are developing physics-informed neural networks, PINs, that incorporate physical laws directly into the learning process. These can solve complex partial differential equations, PDEs, for things like simulating fluid dynamics or heat transfer, sometimes even solving inverse problems like reconstructing fluid flow patterns just from sparse sensor data. For high-dimensional financial problems involving complex stochastic processes, methods like the deep backward stochastic differential equation, BSDE, are combining deep learning with advanced mathematical finance techniques for unprecedented analysis capabilities.
Even finance.
Even epigenetics. Deep neural networks are being used to train highly accurate epigenetic clocks based on DNA methylation patterns, allowing scientists to precisely measure biological aging and study factors that influence it. It's truly enabling a new era of data-driven scientific discovery and accelerating progress across the board. And this will inevitably filter into industry. Institutions like MIT, for example, are explicitly gearing up research programs to transform manufacturing processes using these advanced AI techniques.
Wow, what a journey through the absolutely incredible world of deep learning. It's mind-bending, from giving computers sight and the ability to understand language and context, to designing potential new drugs, discovering materials, and even predicting the weather with unprecedented accuracy. It's crystal clear that these breakthroughs are changing pretty much everything.
Indeed. It's been a rapid evolution. Deep learning has grown from being a collection of complex algorithms, mostly confined to research labs, into an indispensable, pervasive force. It's fundamentally reshaping entire industries and subtly altering our daily lives in countless ways. The pace of innovation is just staggering, and as we've explored today, the impact is truly profound and multifaceted.
Yeah, we covered a lot. Just to recap the big ones, we started with the foundation of advanced neural networks themselves, that deep layered architecture.
Right, learning those hierarchical features. Then came convolutional neural networks, CNNs, giving computers the power of sight for image and video understanding.
Followed by recurrent neural networks, RNNs, and their successors like LSTMs, which brought memory and the ability to understand sequences crucial for language and time series.
Then the creative spark with generative adversarial networks, GANs, and now diffusion models, enabling AI to generate novel, realistic content.
And finally, reinforcement learning, RL, allowing machines to learn optimal behaviors through trial and error interaction with their environment. It's an amazing toolkit.
An amazing and rapidly expanding toolkit, yes. Each breakthrough built upon the last, unlocking new capabilities and applications.
It's a technology that is becoming deeply embedded in our world, often unseen, as you said, but always there, working, learning, and evolving.
That's right. And as deep learning continues to weave itself ever more tightly into the fabric of our world, maybe here's a final thought for you, our listener, to consider. How will our own understanding of human intelligence evolve as we continue to build machines that can learn, create, and adapt in ways that increasingly parallel and sometimes even exceed our own cognitive abilities? And perhaps more importantly, what responsibilities do we collectively have in guiding that evolution thoughtfully and ethically towards a future where these powerful tools truly benefit all of humanity?